Hello and welcome again to Physics 264 Pre-Lab Tutorials. I'm Dr. Steve Brule. Today we're going to study microcontrollers one last time and we're going to simulate a rotary switch. We already have a program that does that for us, and let's take a look at some of these commands. First of all, we've got, as usual, we've got some introductory things to get this chip just working that for example, we have to create some variables that we're going to use. We have to set port A for input now. Last lab we only had output, and we're setting ports B for output. And then there are various chip settings. This is very important. We're setting n equal to -1 before we get started into the meat of our program, and you'll see why that is in a second. Okay, so here's the flow chart over here, and let's just march through the flow chart and see how this program operates. We'll start our switch program by telling the PIC to check to see if the input from the switch, we're going to have a switch on this PIC, and it's going to look for the switch's state on port A pin 1, which is RA1, and as soon as that goes high, then it'll know that we've depressed the switch. So this is an if statement. It'll test if the switch is pressed. If it hasn't been pressed, it just goes back and tests it again, and then it tests it again about 1,000,000 times a second. And then as soon as you press it, it says, finally, I've been waiting my life for this button press, and it says yes, and it goes to the next statement. So it jumps over the go-to statement, which was bringing it back to start, and goes to this next statement. And the next statement, if the switch is depressed, is debounce. And the reason why we need a debounce is because whenever you press a button, the button doesn't have a sharp, you think that it went from 0 to 5 volts instantly, but what happens is as the contacts of the switch get close, they call this bounce, but there's a electrostatic discharge because it's the two contacts are so close together they can have a tiny little spark, you won't even see it, and that's what is happening here. And you also have mechanical bounce, that when the switch hits the metal it can bounce up and fall back. That's what it looks like, but I think most of that is this electrostatic discharge that happens right when you're making the switch contact. And this happens over the course of maybe 1 millisecond, or maybe even less than that. It's very quick. So what Buzz has done for us is he wrote a little program that just delays the program and waits for that to get over with. So that's just a sort of a housekeeping thing we need to do, otherwise our switch won't function properly. That's what you always have to do on these kind of things. Okay, the next part of the program, we increment our dummy variable. Remember we had set it at -1? Well, now we increment it by 1, so it'll go up to 0. And then from then on, it's just going to go from 0 and cycle through these numbers that we're going to tell it to go through. Then it'll test to see what n is. And once, if n hasn't made it up to 4 yet, if it's no, it skips this statement right here and turns the LED that corresponds to the number that n is. And I'll show you how that happens in a second. So there will be a set of LEDs that goes on for n equals 0, n equals 1, n equals 2, but then once n equals 4, then it's the answer to this if statement is yes, and then it sets n back to 0 again, and then it turns the LEDs on that correspond to n equal to 0. So let's look at specifically at those commands. So the BTFSC command is going to test if n equals 4, and you think it's testing if n equals 2, but what it's doing here is that 2 is the second, is bit number 2. So here's bit number 1, 2, bit number 0, 1, 2. So it checks that bit, and when that bit goes high, then n is equal to 4, because it's the binary number for 4 is with an n, 1, 0, 0. So that's why that's a 2 there and not a 4. It's checking the bit number 2. So if the bit is high, that means n is 4, then it's going to clear. Oh, well, I'll tell you. Yeah, I go to the next one here. Then it clears. If it's high, then it resets that number back to 0. And if it's not 4, then it's going to go right here, and it copies N into our working register, which is what we have to do whenever we're moving numbers around inside our microcontroller. Then we call the LED subroutine, and this is another subroutine that Buzz wrote for us. And what that does is it adds whatever is in the working register to the program counter. So if there's a 0 in the W register, then it doesn't add anything to the program counter, and you just go to the, I don't know why that always happens. You just go to the next statement. But if there was, say, a 1, if n was equal to 1, well, then it's going to add that to the program counter and skip over this next one. And if n is equal to 2, it's going to add, well, you see what's happening. It's skipping over these 2. And if it's 3, it skips over those 3. And then once what the actual command does is it sets whatever these numbers are that you have set, and we've intentionally put them on the wrong pins. So this right here would put pin 0 or bit 0 high, and that so if we had a light or a LED attached to the B not register, but the forget the name for it, but the B output. So the if we had a LED on that output, it would go high, but our LEDs are on, I think, 6, 7, 5, 6, 7, so not 0, 1, 2 like it's showing here. So you'll have to change that around a little bit. So if you put, say, if you did have an LED on bit 0, 1, and 2, if you had a 1, 1, 1, it would turn all those LEDs on. But this doesn't actually turn them on. It just puts this number into the W register. And remember, we have to keep putting things into our working register if we want to move these numbers around. So it moves whatever number that you put in here. So say you wanted yellow is going to be, 0, 1, 0, and then so your yellow is on that pin. So then it puts yellow into the W register, and then we move the whatever's in the W register to port B to turn on the LEDs. It's quite a process. This is machine language. Okay. Then, so we've turned on whatever LEDs we want, but now we don't just go on and wait for the switch to be pressed again, because we have to first wait for it to be unpressed. So we want to see if the switch is released, and if the switch is still high, it's going to cycle through this if statement. So what happens is when you push the switch, and you might think that you're pushing it really fast, but you might hold it on for a tenth of a second or something, and that's many thousands of cycles through the microprocessor. So it doesn't want to start looking for if the switch is depressed again while you still have it on, then it's going to go into the next thing. So we have to slow the program down for a human being to be able to press this. So then this statement right here is going to keep cycling through itself until that switch goes to low. So once that switch is released and we've got a 0 on that input port, then we've got a yes here. We debounce the switch again and start all over again. Okay, well, let's look at how we're going to set up our microprocessor lab programming environment. First of all, just like last lab, you open it up before you open the project. Then you open the project within the program. And we're going to have a folder for you, 3 for section 1 and 4 for section 2. And you open up the switch program that's sitting in there for you. And this time we've got your environment all set up, almost. We've got it set up as much as we could to make it as easy for you to do this lab as possible. But there's one little thing that you have to do. So this is what it'll look like when you open it. I'll point out, here's the program itself, and then over here we used to have all these registers, and there were like 30 of them, and most of them didn't make any difference to us. So what I did is I went in and found a way to just display the registers that are of interest to us. So we're going to watch these 5 registers and how they change as we march through the program. This is the, and let's familiarize ourselves with each register. The PCL register gives the current command that's about to be implemented. The W register, as we've talked about before, is the working register that we're moving numbers in and out of inside the microprocessor. N is the dummy variable that we're incrementing in our program. And port A, we've just chosen to have as our input port, and we're only going to make one of our ports active on the input, and that'll be bit 1. It looks like that's bit 2, but this is bit 0, so that the second one is bit 1. So that's the bit of port A that we were going to put our switch on. And port B, as we had last lab, is our output port. And I think we've set that so that we can output on any one of those that we want to. This is a way that we can simulate the button within this program. So we've got a button in the real world, but how are we going to make a button inside this program? You do it using a stimulus. We're going to stimulate the program in some way. And the way we do that, this is that same window, you have to press asynchronous because that means that the switch is not synchronized with the program. It's waiting for some outside human being to switch it on or off. That's asynchronous. Okay, and then you need to set this to RA1 so that that switch is going to toggle the state of that pin up and down. I should say that bit, and the action is going to be toggle. So you have to select those two things, and then whenever you press this button right here, you're going to toggle it either on or off. So this is what your environment will look like once you've set this up for yourself. Okay, let's look at how we're going to step through the Rotary Switch program and record our observations. So first of all, I'm going to suggest that you comment out our oh, I did the wrong one. We should have commented out the debounce here and the debounce here. So comment out the two debouncing routines, because those are these things that's a delay program, and every time you would go through that, which you'll go through it 5 or 6 times maybe, and you don't want to have to like press that play and then get out of it and all that. So it just makes it a little bit easier if you comment those out, just for our debugging step through. In the real life, we need that debounce for our switch to operate properly, but in the program it doesn't need that. Okay, and don't forget to click Build All when you make any changes in your program. Step down. Okay, so we'll step down to the start of the program just like we did last week, and it should be program counter number 12 that's about to be, this is number 12 that's about to be executed once we click step into. So we click step into, and now we've gone from 12 to 13. And what happened? Look at that. The program counter went up to 13, and that's all that happened. It went to the next line. Oh, and what it's doing, it went to this line because this is an if statement. Remember, we learned about that. It's an if statement. It's looking at port A, pin 1 on port A, and if it's not high, it goes to this next statement, which goes back to the start. But if it is high, then, oh, but now, before I go to talk about what's happening, we're going to record every one of these steps that we observe as we step through the program. So what we just observed is program command number 12. We saw that the program counter went to 13, so I'm going to record any changes in my registers that I observe over here in this column. And then in this column, I explain in words what happened. So the program checked the state of the switch, and since it wasn't equal to 1, the program advanced to the next line, which was line 13. Then I click step into again, and I just executed line 13. See, I executed line 13. The program counter went to number 12, and I'm telling you that the command number 13 sent the program back to the command 12 to check the state of the switch again. And we could do like 1,000 of those if we wanted to, but who wants to do that? It'll cycle through that forever until it sees that that switch that we have, that stimulus, is high. So to click that stimulus high, we just press that button right there. We just click on it, and then Now when we execute that start command, the BTFSS command, instead of going to the next line because it was 0, now it is 1 because we just clicked it, and it's going to jump. It jumps over the debounce routine because I've got that commented out, and it goes to the next line. So it's going to line 14 instead of line 13. So I wrote down the PCL went to 14, port A went to 2. So port A is now, you think it should be 1, but remember it's bit 1. I can't follow that right there. Bit 1 is what went high. The last one is bit 0. So bit 1 is high, but that's the number 2. That's the binary number 2. So that's why port A is saying that it's 2 and not 1. If I had had my input on port 0, which I don't think you can have on our A input, then it would have had a 1 there. Okay. So I recorded all those changes down here, and see here it was port A was 0 before. So port A changed, and so did the program counter. So there we are. Let's click into it again. We're on this next command that says incf. Do you know what that's going to do? So when we jump from here to here, we just executed line 14, and that incremented n. So n was at -1. That's -1, I guess. Yeah, -1 in, what do they call that? Complementaries. It's the way you give negative numbers with binary. So that's a -1, and it went to 0 now because we've incremented it once. Okay, and then so on. So you're going to go and increment your way through this whole program until you've gone through until n is equal to 4, and then it starts all over again. Okay, and now we're on part 4, where we're going to program or burn the program into the chip that we've just marched our way through, and we're going to verify that it operates as programmed. So first you'll need to breadboard your PIC, and the difference from last week is that we've got a button now on RA1 to provide input. Last week we had no input, it was just operating on its own. And we also need 3 resistors here instead of 1 because we're going to have more than one LED on at a time, so you need a separate resistor for every LED. And it'll look something like this when you breadboard it up, with each one of the LEDs using its own resistor, and you can put your different order of colors, whatever you like. Don't forget to put your debounce before you burn. Make sure that you have turned your debouncing routines back on. So remember, we had commented those off when we were marching through the program, so we wouldn't be annoyed by that process. But now you have to turn them back on so that the switch actually operates properly. Okay, so then you burn the program into the PIC, put it back into here. Make sure that when you're taking this off, especially when you're taking it off, be very careful that you don't bend those chips, pins. So use your screwdriver to pry that up. Very important. We had somebody last week who, I won't say who, but they put their PIC in backwards and it burnt up. So don't do that. Make sure that your pin 1 is always where it's supposed to be. The pins are highly susceptible to static electricity, so try not to touch any one of those pins, and be sure you don't have any static electricity on your hands. And if you're moving it around, put it on one of those. Okay. Alright, so you're going to verify that it works the way it is, and just observe that. Now you're ready to reprogram your PIC for alternate operation, which is the climax of this lab. What we want you to do is go through that program. Here it is, from start. You'll have to change some program steps in here to do a different operation. And here's the operations we want. On the first button press, only yellow goes on, then yellow and red on, then everything is off, and then everything is on. Then only red is on, everything is off, only green is on, then only yellow. Oh, and then it should after that, it should cycle back into here and keep doing that over and over again. So see if you can make the program do this. Once you're done, call your lab instructor or TA to demonstrate your accomplishment and receive praise. We hope you've enjoyed this show.